So what we're going to talk is basically a foundation of all the theory of p-adic Hodge theory. Or if you find in the literature, if you find something called p-adic Hodge theory, or some phi gamma modules, or especially if you find the name Fontaine, probably is in this spirit. This theory certainly, to study number theory, we have this local global principle. So, and then you need to study the p-adic representation. And then if you want to study the representation of local fields, and then you need either one is L is not P and there is L-adic representation. That's so-called ASARC homology. So that was founded by Gothendik during the 60s and also and Delhi and others. And that is a very hard topic, but it's very but still easier than these p-adic ones. So if L equals P, that is always the hardest part. So if you want to analyze some representation, you need to study the L equal to P part. And this is founded by Fontaine and all this theory. But first, in the very beginning is the theory of Coates wires and also Coleman's power theories, if you read the book of cyclotomic fields. So that's the very beginning, and then Fontaine founded all kinds of rings. So here we need to talk about the very beginning, but I will not talk about what is bit RAM or bit Chris or other rings, but this is the very beginning ones. And then this phi gamma module theory. So this section 3. And if you want to find some introduction to this Fontaine theory, so most of the references are in French because the French guys don't want to write in English. But then there is so I'm writing a book with Fontaine, and but the manuscript you can find in my webpage, and I think in my notes there is an address there. So, but it's not done yet. But you can see all the basic material I'm going to talk about today. Okay. So here we have. So first what I want to talk about is Fontaine rings. So there are many rings. So basically there are. So what we're going to study is this. We have QP, and we have a finite extension of QP, so it's K. So here we have QP bar. So here is GK, right? As I explained the last time, we also have this so-called K infinity. This is just K delta P to the infinity. Or even I can write a little bit better than this. So we have QP, we have K, and we have some Kn. So Kn, or you can say it's just K plus mu to the Pn. Okay, so then we have this K infinity. So it's K mu P to the infinity. And then this is Q bar. So this is finite. So what we will study basically is to study the properties, especially representations of K, of GK. So this is GK. And this one I always write down as H of K. So this is gamma K. And oh no, this one. This is gamma K. So this I write down as gamma n. So gamma kn. So maybe I just write down as gamma n. Okay. So so first is this picture, but then what we study is, so there are fountain rings. There are many kinds of fountain rings. So first is a series of rings of characteristic p. So p is the same p. Okay. So what we have, the first thing we want is this so-called E tilde plus. And in the literature, so there are two sets of notations. Commerce uses this kind of notation because he wants a unified structure. But when Fontaine was first developing this story, so he didn't have a unified picture, right? So he usually write this as R. So what is this? This is just the projective limit of this OCP over POCP. Or you can say it's also the projective limit of OQP bar over POQP bar. Okay, so what is this project limit? So basically, if you have A is a ring of characteristic P, then you have RA is just this A, but the transitive map is X goes to X to the power P. Okay, it's just using Frobenius to get this RA. So here is the same. Okay, so why this is R? So it's actually is R OCP over POCP. Or you can use this. So if you write down as these elements, you can write down like this. It's X sub n, right? N contained in n. So Xn is contained in OCP over POCP. Because of that condition, so you have Xn plus 1 to the power P is Xn. So that's the element in E tilde plus.
Where is the untaken pro limit?
Which one? This one?
Yes.
The limit, you mean the transitive map? It's just X to the X power P.
I see.
Okay, so you just say, if you write AN or equals A, say AN plus 1 goes to AN is just X goes to X to the P. Okay, so so if you look at write down as this, you can have this. Okay, so the trick is you have one way you can write down this, and then there is another way to write down this. So it's sub n. So y subscript is y is a superscript. So this is xn is contained instead of in the quotient ring is just in here, and then xn plus 1 to the p is xn. Okay. So these are the two ways to write down this. And there's a bijection. How to make this bijection? So say if you from here to here, you just take modulo p. You get this. But what about, how do you get this xn? Is this xn canonical? So xn is actually this. You just take the limit k goes to infinity. And then for this xn plus k, you can take, so here you can take a lift of this in OCP. But this lift, there are many lifts, right? So for example, any lift, and then you take to p to the power k. And then this converges. So this converges, and this is a canonical choice. satisfy this condition. Okay, so this is a ring. So this is a ring. Actually, it's a perfect ring of characteristic P, and also the ring structure here is easy. If you using this, you have plus and multiplication is easy to write. But if you write in this form, then the ring structure is a little bit difficult. So you say x is xn, y is yn. Okay. So if you have these two forms, you see x plus y n is just xn plus yn. X times yn is xn yn. This is just a project limit. But for this one, it's a little more difficult. So for the upper limit, so x plus y to the n, so this is not xn plus yn. Okay? So this is actually is this. You need to take the limit. So it's xn plus k plus yn plus k and to the p to the k. And then this limit, this is the sum. But xn, this is the same. Okay. So this is, you get the ring structure. Now having this, what we know is E tilde is a valuation ring. What is a valuation? So we have this valuation is just Vp x of 0. So by this valuation, this is a valuation, you can check it's a valuation, and then you get a valuation ring. But this valuation is not discrete. So of is P, and was a perfect. And you can also know what is, so we get E tilde is just fraction field of E tilde plus. Okay, so the residue field, this is just Fp bar. It's just Fp bar. It's just a algebra closure of finite fields. So this is E tilde. And also we have GQP x on E tilde. Right? Say you can x on this element because you can use OQP bar over OQP bar, and then it's actually complement wise. So you can x on this. So first we have this ring. The second one we have two elements. One is epsilon. No, this is not D. One is epsilon. This is 1, epsilon 1, epsilon 2. So this is contained in E tilde. Okay, so we want this is not 1. Okay. Now this, because of the condition, this implies what? Implies this is a primitive p-nth root of unity. And this is uniformly chosen. So this is E epsilon, and pi bar is just epsilon minus 1. 1 is just the identity element. So now it's an exercise. You can find this. E certainly is a unit, but this one you can find this is p over p minus 1, the valuation. So you need to use this formula to find it. So this is p over p minus 1, this is bigger than 0. Okay, so these are the two elements. Now, for k, so we have a set of fields. One is rings of ek. So here this E and then this sub k. So this sub k is the same. You have xn. Instead of xn contained there, so you have xn is contained in OK infinity over p for any n. Okay. And then you have this xn. Now xn is contained in okn over p for n sufficiently large. So this is another. So, this for any k you have this. Now these are rings, and then you have field. It's just pi. You just inverted pi. Okay, so you have this or pi bar, yeah. So, and then we let E is just all this k, ek. So we have this. Okay. What do we have? This is nothing. You need a proof. This nothing about separable closure of EQP. But this EQP, this is also very easy. It's just FP. And then pi bar. It's just a Laurent series ring, the field of Laurent series over FP. Okay. So this is separable closure of EQB. And we have this is EK, the radical closure. So because this one, the Frobenius is not bijective, so you need to take the radical closure, so you get EK. So if you get tilde, then you make a radical closure. And the same as here, E tilde is nothing. The E tilde we define there is just E radical. Okay? So it's just a radical closure of E. So the theorem, the main theorem in this is Fontaine and Winterberger. So you see, before he proved the cell conjecture with Carr, so Winterberger did have a large gap of not publishing anything. So, so this is his thesis as a student of Fontaine about. So this is called field of norms. So he proved this, and then for many years, maybe he studied some big problem, and at last he proved the cell conjecture with Carr. So probably maybe in Korea it's better. You can like stay for a while not publishing, but in China this is not the case now anyway. Yeah. So what is the half? This is called the theory of field of norms. Field of norms. But then this is okay. So what we have is this Galois E over EK is nothing but HK. Okay, so this is the Galois extension, and the Galois is just HK. So that means, so when you study G of K, so using this characteristic P, you get you know this is an H of K structure, and then in another part is this gamma K structure. So you get some gamma actions. Okay, so this is these are the rings of we want to know characteristic P. Now let's talk about rings of characteristic 0. So then there are many other rings. So the first one, what we want is A tilde plus. It's just a W E tilde plus. So W means weight. Okay, because of all this ring is perfect. So you have the weight ring, and this weight ring is canonically isomorphic to each other. So you only have one weight ring. So A tilde plus is just the W of this. So A tilde is just the W E tilde. And then we have this B tilde is just this A tilde. Because this, what is the weight ring? So so if you have R, is perfect. It's a perfect ring. Okay. So it's P ring. You know what is WR? WR certainly is unique, characteristic 0, and then absolutely unramified. So what it means absolutely ramified? So this just means i.e. P is a uniformizer. Okay, and residual field R. So basically, if you have a ring R, what you want to know the property of WR, so it's classified this. So this is unique. Unique just means unique up to canonical isomorphism. So only one isomorphism. And also characteristic is 0, and also absolutely unramified, and the residual field is R. So this is the same thing here. So if you want to find the fraction field of this, you just need to invert P, because P is the generator of the prime idea. Okay, so this is a fraction field of A tilde. Okay, and then we have AK bar, AK tilde. You can the same thing as EK. So it's AK tilde, and then 1 over P. Okay, so now let's see what is the element if X contained in A tilde. So we know X, if you write a weight ring, so it's X0, X1, something like this. X. So you can write down like this. I don't want to specify the last one, but you can also write down like this. So it's K is bigger than 0, P to the K, and X of sub K. So yeah. Otherwise, actually you need X to the K to some power if you write down this X to the. So if you use X, the K component here is XK. So this sk is not the same as this one. Okay, so maybe I just write on x equals this. So this one, what is this? This is called the Teichmüller lifting of x, sk. So it's just xk and 0. So the other components are all 0, and just the first component. So this is the Wittering. So how you get this? So you have x is this, then you have GQ p-adic on x. So this is easy. Say gx is just p to the k gsk. And you have phi action on x. So in characteristic P, then the phi is always the Frobenius. You always have this. So for this one, you can also have phi of x sk to some power p. Okay? So that's the thing about the action we have. And the other thing we need to know is about the topology we have. So what is W? W, say, for any R, for any ring R, so this is bijectively not a ring isomorphism, just a bijection of R to the N. Okay? N just means all the natural integers. So there are two topologies here. So one is you think R is discrete. You have this bijection, right? You think R is discrete, and you take the product topology. Okay. And the other is you have topology in R, and then you take the product topology. So there are two topologies in here. So this is for general R. For here, two topologies. A theater. So again also on B theater. So one is called p-adic topology. So, or you can also say strong topology. In this, a neighborhood at 0, a basis of neighborhood at 0 is just pk a theater plus. So a basis of neighborhood. Okay. The second thing is natural topology. Or you can say the weak topology. For this one, you have the neighborhood is pk a theater plus plus you need to think about the structure of this E theater. This E theater, say, is M E theater to some power k, for example, and then and then you take a theater, something like this. Okay. So because this is not discrete variation, so maybe you need say here we need like just pi bar to some power n. Okay. So pi bar is just a Teichmüller lifting of pi. So these are the two topologies, and often people make mistakes in these two topologies because there are many people claim he proved very good results, and then later on found use the different topology. Okay. Now we have two elements. Again, we have two elements. One element is this. It's just 0. Okay, so it's just Pasch-Mie lifting of E. And the other element is pi is -1. So this is -1, and then you have, this is not 0, okay? You have some element here. So now you have phi action and gamma action. So phi, this is easy. So G action. Now this is G action. Because of this, you can say this is to the chi G. So here chi is the same thing as you have. If we have GQP, we get gamma QP -1. G pi is 1 plus pi to the chi G -1. Okay, so actually, yes, this pi is the same as the t we have last time. We just change the variable from pi to t. Okay. So this is the second thing, and also the actions. So the third one is we have this AK. So here we have AK theta, but again we can have AK, and also we can have BK. So what is AK? So as we just claimed about this, AK theta is absolutely unramified. Absolutely unramified discrete valuation ring for the residue field is EK theta. So this one is the absolutely unramified discrete valuation ring of characteristic 0 whose residue field is EK. Because EK is not perfect, EK theta is. So EK theta is easy, we just take the Wittering. So this is not so unique, but we can say there exists a unique one. And this is contained in maybe B theta. Anyway, so it exists a unique one. And this kind of ring, absolutely unramified discrete valuation ring of this satisfy this. You can also call this the Cohen ring. It's not the Wittering ring, but the Cohen ring of EK. Okay, so we get this, and then we get BK. It's just AK, the fraction field of AK. So now we can let B. I want to get all this BK. But then this one is not complete. So we take the completion. So this p-adic completion. So this means p-adic completion. So we get this is B, and this A is just B intersect A theta. So we have all these rings. But what is this? This is just like we have AQ, so K is QP. What do we have? So we get AQP plus is nothing but GPT. Okay, you just need the, and the what is AQP? AQP is nothing but this. You get GP, and then you get 1 over pi. You take the p-adic completion. Or you can say is this n is contained in the an pi n. An goes to plus infinity, it goes to 0 if n goes to minus infinity. Okay? So this is AQP. And BQP, so an is contained in GP. BQP is just the same thing. Instead of an in GP is just an in L, and then you want bond it. Okay, so that's that is the ring we want to construct, but after all, we need to relate it to the one we studied before. So let's recall, what is OE? See, OE is nothing but ANTN. AN is contained in L. AN goes to 0 if n goes to minus infinity. Or you have E. So it's A is in Z. AN is contained in L in bounded, and AN goes to 0 if n goes to minus infinity. So you see, if you replace this pi by t, so you can see this one is nothing but your tensor product over ZP of this AQP. And this is nothing but O is L, your tensor about QP and BQP. Okay? So that is the one we want to study. And because of this, this is a coloring. So again, you have this one. See, what is this? This is nothing but this BQP, or this unramified closure of BQP. So you don't have the maximum unramified extension, abelian extension of BQP. Okay, so it's you get this Galois B over BK is just HK, because you only have a residual extension. Other things you don't extend, so this is just E over EK. So this is just H of K. Okay. So what are these notations? These two sets of notations. You have lambda, it goes to lambda tilde. So you have something, you have a tilde, something have not. So for example, lambda is EK, AK, BK, etc. So all this is just makes phi bijective. Just means in here phi is not bijective, but in the tilde case phi is bijective and then complete. So this is the rings we have. Okay, so The last thing we want to know is so-called overconvergent elements, the ring of overconvergent element. So it's also characteristic 0. Maybe it's 4. And then this one is, you just say a tilde 0R. I don't need maybe R1, R2, but I just say this, is this. So it's X, you can write that as X is K, P to the K, X to K, right? So it's in a tilde. And you want some notations. For example, limit K goes to plus infinity, Vp S of K plus K over R is plus infinity. But then this one you can also find this is about this. It's about so we have A0R first. It's just this intersect A. So you have AK 0R. Then what do we have here? Say AQP 0R. If you tensor again with DP, or I think maybe it's PQP. If you tensor again with L, oh no, QP L. This is the one we studied. Okay, this is again the one we studied. So this is we call overconvergent element. But this looks like different. But you need to change a little bit, do some computation. You will find this is again the same thing. So this is so-called ring of overconvergent elements. Okay. And then you have so B. What is BK? You just say, I think you just take 1 over P. It's just this. And then you have the ring of B dagger. QP is just the union of all this R BQP 0R. So this is dagger, the field of overconvergent element. So these are all the elements we give. So this is Fontaine rings. So that's, as I said, we have a lot of notations. Okay. So now we move to the second part. Maybe we can have this. Yeah.